Hey folks, my name is Nathan Johnston. Welcome to Lecture 7 of Vector Calculus, which is all about curvature of a curve. So the idea here is you've got some curve in space and you want to quantify or measure how bendy it is, how quickly it changes direction. Okay, and I want to distinguish this from what we looked at in the previous lecture video. In Lecture 6, the previous one, we looked at the angular speed of a path, which was, okay, now you've got a particle or a path moving around space. How quickly is it changing direction? And the difference there is you were interested in motion, right? There was a particle that was moving around, and you were talking about how quickly it was changing direction. But now we're forgetting about the particle. We're only looking at the curve that the particle traces out, and we're going to talk about how quickly it changes direction, regardless of how quickly the path itself was moving, or regardless of how quickly the particle itself was moving. Like, it doesn't matter now whether the particle was going super quickly to trace out the curve or if it was going really slowly to trace out the curve. We want the curvature that we're going to compute in this lecture to be the same regardless. So how do we do this? Okay, and the setup here, what we're going to do is we're going to sort of mimic what we did in the previous video. We're just going to change time to unit of distance. Okay, so in the previous video, what we did was we measured the angle between sort of nearby velocity vectors, and then we computed the rate of change of this with respect to time. Like, as time changes a little bit, how much does the angle between the velocity vectors change? We're going to do the same sort of thing here, except instead of saying, okay, if time changes a little bit, how much does the angle change? We're going to say, okay, if the distance along the curve changes just a little bit, how much does the angle between them change? In other words, we're going to be measuring the instantaneous rate of change of the angle between the, velocity vectors or tangent vectors per unit of distance that's traveled instead of per unit of time that's sort of gone by, like in the previous lecture video. Okay. In other words, what we're going to compute is this limit here. We're going to compute the limit as delta L goes to 0 of delta theta divided by delta L. So delta theta, that's the angle between two nearby tangent vectors, and delta L, that's a teeny tiny change in the amount of distance traversed along the curve. Okay, so that's our definition of curvature. Maybe another way of thinking about this, though, is like what we can do to sort of leech off the things that we did in our previous lecture video is remember that we've seen how we can come up with a parameterization of any curve that's with regard to this L parameter, the distance traveled. Okay, in other words, there's a parameterization out there that has the property that this L really is time, like distance traveled is time travel. This is what we called parameterization by arc length just a few videos ago. Okay, so another equivalent way of defining the curvature of a curve is, well, just come up with some parameterization by arc length of that curve, and then compute the angular speed of that. The angular speed of a parameterization by arc length is going to be what we're calling curvature up here because delta L is delta T, so we can just leech off of earlier stuff. Okay, so we've got a working definition, just a couple notes before we get running with it. And the main thing that I want to talk about is the notation that we're going to use for it, okay? Whenever I talk about kappa of L, well, that means this curvature that we've defined up here. It's this limit up here, and it's a function of L. It's a function of how far along the curve you are. That's what that L parameter is. It's this distance traveled so far parameter that we've talked about in a couple of the previous videos. Okay, sometimes we're going to abuse notation a little bit and call it kappa of t, and we're going to do that when we have some particular parameterization or some particular path in mind that traces out the curve that we're talking about, and it'll just be easier sometimes to talk about the parameter of that parameterization or the parameter t of that path. Okay, so if I say kappa of t, like really it doesn't depend on time. There is no time here. It's just a curve. Really, like what's going on is we relate this t to L in the usual ways via this parameterization by arc length sort of stuff. But it's going to be, convenient just to write it like this. A lot of the time when we're actually computing it, we're going to compute it as a result of, this time parameter. We're going to have some way of tracing out the curve, and we're going to compute it in terms of the time parameter. Okay. But anyway, okay, so how can we actually compute this thing? Okay, how do you compute the curvature? And I mean, the definition gives one way of computing it. Okay, like you just follow along what the definition says. It says, okay, come up with a parameterization by arc length of that curve, and then just compute the angular speed of that parameterization. Okay, and like we've seen how to do all of these things. Like we learned how to do parameterization by arc length 2 lectures ago, and then we learned how to compute angular speed 1 lecture ago. So yay, we can do this. We can compute curvature. Except there's a bit of a problem there, and that is, remember, computing parameterizations by arc length really, really, really sucks, okay? Like, we don't sort of have a systematic way that actually works in practice. Like, we showed that theoretically, yeah, every curve has a parameterization by arc length, but how do you actually compute it? Well, I don't know. You've got to do this horrific, ugly integral, and then you've got to invert the function. Like, these are things that you can't actually do explicitly most of the time. Okay, so we're going to try to sidestep this issue. We're going to try to come up with a way of computing curvature that avoids the parameterization by arc length. Okay, so here's the setup. Okay, so suppose that you've got any curve, okay, or sorry, any path f that's tracing out the curve. So f is just some parameterization of the curve, and then f tilde, that's a corresponding parameterization by arc length. In other words, it's this parameterization f tilde of L equals f of t of L. Okay, this is this way of constructing a parameterization by arc length that we talked about 2 lectures ago. Okay, now when we have that, we can start asking, okay, well, like, if I were to compute the angular speed of this quantity over here, and thus the curvature of the curve, what would that look like? Okay, like, what would that look like in terms of this stuff on the right-hand side? And let's start trying to work through this sort of idea here, okay? So, how do you compute the angular speed of a path? Well, you need to know about its unit tangent vector, okay? And the trick that we're going to use is that these two paths, f and f tilde, they're tracing out the same curve, so they have the same unit tangent vector, okay? And that's all I've written down over here. I'm saying the unit tangent vector t tilde of f tilde, well, it's the exact same as the unit tangent vector of f. Okay, and I mean, that makes sense geometrically, right? Like, if I've got one particle that's moving around a curve and then another particle that's moving around a curve, maybe faster or slower, doesn't matter. The unit tangent vector, the tangent vector that's scaled to have length 1, it's the same for both of them because the direction of the curve itself is the same at every spot, and we've sort of renormalized out the distance or the speed of the particles. Okay, so all that's left is the direction, and the direction is the same for both of them as long as we adjust the parameters appropriately so that the particles are actually at the same spot on the curve. Okay, great. When we do that, great. Now what happens when we plug into the relevant formulas? Okay, so let's talk about how we would compute the angular speed of this f tilde, of this parameterization by arc length. Well, what we would do, angular speed theorem from the previous lecture video was our way of computing the angular speed is you compute the length of the derivative of the unit tangent vector. So that's all this is. This is our formula for angular speed of f tilde from the previous lecture video. Okay, and just to be clear here, omega, that means angular speed, but because it's angular speed of a parameterization by arc length, this is also kappa of L. It's also the curvature of the curve. Those are the same thing when you've got a parameterization by arc length. Okay, but now what we're going to do is we're going to try to turn this quantity into something that just involves f itself, that could be computed directly from f. And here's the trick. Okay, what I can do is, well, I would like something that's not in terms of L anymore. I would like something that's in terms of the parameter for f. In other words, I want something that's in terms of t. Okay, and to make that happen, I can use the chain rule, right? Okay, d t tilde by dl, that's the same as dt by d little t, and then d little t by dl, right? Like, it's sort of the standard chain rule mnemonic that's not quite true, but it's mostly true, is that, oh, these dt's, you can just sort of imagine them canceling out with each other, and then, oh, you just got a dl down here, and then the only other slight wrinkle here is that, oh, I've got a, a capital T vector here, whereas over here I've got a capital T tilde over here. I mean, those are the same vector, okay? They're the same thing, so it's all okay. So yeah, it's just basically the chain rule gives you this equality here, and then we're going to flip this around a little bit. We're going to say, okay, is this a computational formula that I can actually use in practice yet? And this piece here, yeah, I know how to compute that. I know how to compute dt by dt. That's just compute the unit tangent vector. Easy. Take the derivative of it. Easy. What about this thing over here? Ooh, this isn't quite easy, right? To compute this, I would need to know t as a function of L and then take the derivative of it. And oh shoot, if we think back to when we did parameterization by arc length, computing t as a function of L, that was that annoying thing where we had to invert a function and all that, right? And that's exactly the step that we're trying to avoid, because that's the step that you often can't do in practice, at least not explicitly. Okay, so what I'm going to do is I'm going to flip this around. Okay, again, assuming that things are sufficiently nice, you need your velocity function to never equal zero so that you can actually divide by this quantity here, and you need your functions to have nice derivatives for this step to actually be justified. But like sort of like surface level, like you can think of this as, okay, dt by dl, if I just flip that around, divide by it instead of multiplying, now it's dl by dt. Okay. And this, oh, now this is a computational formula, right? Because like on the left here, that thing, that's just derivative of unit tangent vector. I know how to compute that. This over here, dl by dt, I know how to compute that as well, right? This is the length so far function. If I take the derivative of that, remember, I get exactly the speed of the path. I get the speed of f. And I know how to compute that. I just take the derivative of f and then compute the length of that vector. Okay, and then I just plop all these into this formula, and I get something that I can actually compute. Okay, so here now I'm just going to say, okay, well this is just a number, right? So I can sort of pull it outside, and I'm just going to get this here. Okay, I can split it up into a division of two different lengths. Okay, so I get the length of the unit tangent vector divided by the speed of the path, the path f. And yeah, again, the point of this is it's a formula that I can actually use in practice. It's a thing that I know how to compute. Okay, so let's write this down as a theorem. Okay, so put it in a theorem box. Suppose that you've got a path that traces out a curve, okay, and you're going to need it to be a C2 path, okay, because this formula, just like in the previous lecture video, it involves second derivatives. Once to compute f prime, or the speed, or the velocity, and once again when you take the derivative of the unit tangent vector. Okay, you've got to assume that your velocity vector is never equal to zero, your speed of the particle is never equal to zero. But then assuming that happens, then what you do is you compute the unit tangent vector for f, and the curvature of the underlying curve. It's just, well, the angular speed of that path divided by the speed of the path. Okay, so what's going on here? Like this quantity in the numerator here, again, remember that is the angular speed of f. Okay, and down here, that's the speed of f. So like sort of the way you can think about this formula, like what's going on, if you want to compute how bendy a curve is, what the curvature is you take the angular speed and you just divide by the speed. Okay, like sort of what this is doing is you're saying, okay, I've got a particle that's moving maybe really fast and really slow, then maybe really fast and really slow. It's moving around a curve however it likes. If you want to compute how bendy the underlying curve is, you just sort of divide away the component of angular speed that's how quickly the particle itself is moving, okay? Because that part really shouldn't contribute to what we're trying to compute here. We're trying to compute something about the underlying geometry, not the particle moving on that geometry. So if you just divide away that speed of the particle, then you do get something that tells us about the underlying geometry. And that's sort of how this formula works. That's sort of what it's telling us. Yeah. Alrighty, let's do a computational example or two, and then we'll be done. All right. So suppose that you're working with, a circle this time. Okay, so I've got a circle parameterized in this way. So a and b, those are just fixed positive real numbers. You've got a path a times cos bt, a times sine bt, and we want to compute the curvature of the circle. In the previous lecture video, we computed the angular speed of this path. We're computing something different now, the curvature of the circle. All right, but we're going to leech off of some of those computations that we did last time, okay? In the previous lecture, we showed that the speed of the path was a times b, and the angular speed was b itself, okay? Well, what's my formula say? It says once you've got these two quantities, once you've got the angular speed and the speed, just divide them, and you get the curvature, okay? So in our setting, the curvature, it's going to be angular speed divided by speed. Oh, that's b divided by ab. In other words, it's 1 over a. Okay, the curvature of this circle of radius a, right? It's a circle of radius a. It's 1 over a. And this makes a heck of a lot of sense, right? Okay, what's happening here is the curvature of the circle. Well, first off, larger circles have smaller curvature, right? Okay, what this is telling us is that if the circle's radius is really, really big, okay, then it's bending just a little bit, right? Because when a is really big, 1 over a is really, really small, okay? And like you can sort of imagine like in the limit, as a goes off to infinity, like the circle is kind of approaching a straight line in some sense. Like it's so big, you can't even see it curving anymore. Okay, and then in the opposite regime, when a is really, really small, this curvature is going to be huge because, like it takes very few units of distance for the circle to rotate around. Okay, so that makes some sort of intuitive sense. And also, like another thing to note about this formula here that we just computed, this 1 over a, it doesn't depend on b, okay? And that makes a lot of sense as well, because up in this path here, what does b do? Well, it doesn't contribute to the underlying geometry at all. If I change b, it's tracing out the exact same circle. So automatically, right away, curvature should be independent of b. Okay, all B is doing is indicating how fast the particle is moving around the circle. That has nothing to do with the geometry. It has nothing to do with the curve, therefore nothing to do with the curvature. Okay, let's do one final example and then we'll be done. All right, so let's look at a weirder curve. Let's look at, okay, it's a curve in three-dimensional space this time. Okay, so it's a path from some interval -1 to 1 into three-dimensional space, and it's going to be defined just via some ugly formula. Okay, so you can see here what this path looks like, but it's not terribly relevant. Okay, so the question is just calculate the curvature. Okay, so not calculate the angular speed. I don't really care about like how quickly the particle is changing direction. I care about the underlying curve itself. How quickly is it changing direction, like per unit of distance on the curve? Okay, so let's compute the curvature. And for this, I mean, you just go through step by step. What types of things do you need to compute this? Well, you need a unit tangent vector, and to compute that, you need a velocity vector. So let's start off by taking the derivative of each entry to get my velocity vector. 3t becomes 3. 3 halves here comes out in front, turns the 4 into a 6. New exponent's 1 smaller, so new exponent is 1/2. And same thing happens in this entry. 3 halves times the 4 becomes a 6. New exponent is 1/2, and a little bit of chain rule gives you an extra minus sign out in front. Okay, next up, compute the speed. In other words, just take the length of this velocity vector, square the first entry, square the second entry, square the third entry, add all those up and square root the whole thing. You're going to get a square root of 81, and in other words, just 9. Okay, so the particle, it actually is moving along this curve at a constant rate. The constant rate's not 1, though, so the angular speed isn't equal to the curvature here. The angular speed is going to be 9 times too large, okay? The angular speed is going to be 9 times the curvature. Okay, next up, unit tangent vector. It's just velocity vector divided by speed. So just do that, right? Take your velocity vector, divide each entry by 9, and you get this junk here. Next up, okay, we need the angular speed, which is just unit tangent vector, take its derivative, and then compute how long that is. Okay, so when I compute the derivative of this unit tangent vector, the 1/3 becomes a 0 because it's a constant. 1/2 times this 2/3 out in front becomes a 1/3. New exponent's 1 smaller. Similarly, over here, we get another minus sign out in front, canceling the minus sign that was out in front. Chain rule has sort of kicked in twice now because this is the second derivative, and we have no minus sign out in front anymore. So that's my unit tangent vector. Next up, angular speed is how long this unit tangent vector is. And so just something we've already done. Sum of squares of entries, add them up, square root the whole thing. Okay, and let's simplify that a little bit. It's going to be, I can pull out this 1/9 out in front of the square root. Now it's a 1/3 because I've square rooted it. I'm just left with these two terms inside the square root. And you could find a common denominator if you wanted to. I'm not going to bother. All right, so that's the angular speed. But like I said, that's going to be 9 times bigger than the curvature of the curve. So last step, curvature, it's angular speed divided by regular speed. And we already computed both of those things, right? Angular speed divided by regular speed. Just plop it in. Now, instead of having a 1/3 in front, you've got a 1/27 in front, and you're done. That's the curvature of the curve, okay? And like the way that I interpret this, like this is a little bit wonky because it's in terms of t. This is the abusive notation that I mentioned earlier. Okay, the way to interpret this is, okay, my parameter t is coming from this interval from -1 to 1. If I plug some t value into here and get a location on the curve, then plug that same t value into this formula, and that gives you the curvature at that point on the curve. Okay. Alrighty, that's all I've got for you today. Thanks for watching, everyone, and I will see you in a few more days when we start talking about scalar fields and scalar line integrals. So I'll see you then.